Okay, good, yeah. Okay, back to the next session. Normally, this is the most difficult time to sit in a class and listen to a lecture. After lunch, you tend to feel sleepy, right? Yeah. Okay, I'll try to make it not very heavy, okay, so that you won't sleep. Yeah. Okay, good. So, any more questions about what we looked at in the morning session? I know it takes some time to absorb and also grasp it fully. Okay, you need to kind of do it by follow-up reading of the relevant material, right, in order to consolidate your understanding. Okay, so basically we looked at how this models called these convolutional neural networks can be used for classification, task, segmentation, and the object detection. Now we are going to see how they can also be used to perform these other tasks that we are discussing in the morning, like captioning, question answering, and the common sense reasoning, mainly on the image and the video data. If you remember, we talked about this image captioning, where the task is given an image, we need to generate a sentence that describes the content of the image. So, typically this is done using two modules. Okay, the first one is what is called the encoder, and second one is what is called decoder. But this encoder and decoder are different from encoder and decoder we have seen in the auto-set neural network. There it's a compression and the decompression. It is different here. We'll be understanding what it means. Basically, the encoder takes an image as the input, and typically the encoder is one of the CNN models that we have looked at. And if you take the output of the pre-final layer, right, like any of the deep CNNs we looked at, right, that gives a representation of the image in the form of a feature vector. Okay, and that feature vector is supposed to contain all the important information about the content of the image, and that will be given as input to another neural network model called the recurrent neural network model, which is going to be acting as what is called a decoder, and this model will be trained to generate a caption, which is going to be a sentence. Okay. So basically the encoder gives a feature vector representation of the image, and the recurrent neural network based decoder will take this representation as the input and then generate a sentence that describes the content of the image. So we'll quickly see what these recurrent neural networks are. Earlier we've seen this multi-layer feed-forward neural network. Yeah, we'll be seeing how this also will be used for the visual question answer. So earlier we looked at what is called this feed-forward neural network, where typically the connections are from the nodes in one layer to the nodes in the next layer. The recurrent neural networks have a slightly different structure. Here also there is an input layer where we give this the feature vector x. Then there is a hidden layer, but you can also see that the output of the hidden layer goes as the input to the hidden layer itself. Okay, that's why it's called the recurrent connection. If any of you have studied a course on digital electronics, right, you would have studied about what are called the flip-flops, right? There the outputs of some gates go as inputs to the gates. In the same way here, right, outputs of nodes in one layer go back as the input to the same layer. That's why it's called the recurrent structure, and that gives the power to this neural network to represent what is called a memory, right? So if you look carefully, the output of the hidden layer is denoted by what is called the HT, that is the output of the hidden layer at time t, and the output of the model, output of the layer at time t minus 1 is what is denoted by HT minus 1, and that forms as the additional input to the layer. So this hidden layer takes two inputs. One is the external input xt, that is the input at time t, and the output of the hidden layer at time t minus 1, and both of these are used to generate the output of the hidden layer at time t, and then we also generate output of the model itself at every time t. That's what is denoted by the st. Okay, and all of these are kind of vectors, right? And as we'll be seeing later, this will help us to generate sentences, okay, where sentence is considered as a sequence of words. So what is generated but at every time instant is one word. Okay. Typically one uses the conventional activation functions like the sigmoid functions in the standard recurrent neural network, but that has a limitation in handling what are called the long sequences of the inputs, and that problem is known as the vanishing and exploding gradients problem. And a new type of neuron, which is called the long short-term memory neuron, is used in a network where it replaces the conventional sigmoidal neuron, and this will not have the vanishing gradient problem. Therefore, the training of the model is going to be much faster compared to the RNN. So most of the current day deep neural networks, whenever we are dealing with what is called the sequences, right, will be based on this long short-term memory network. So we'll be seeing that a combination of this CNN model and the LSTM model are used to perform this task called the image caption. So you can see that this CNN model, like VGGNet, takes the image as the input. Then we have removed the output layer here. So we take the output of the pre-final layer, which will be one feature vector of some dimension, and that goes as input to the hidden layer of the recurrent neural network. But what is it I want to use this recurrent neural network for? I want it to generate a sentence, which is the sequence of words. Okay. So during training of this model, I have the image and also the caption. Okay. So I pass that image through the CNN model and generate this representation, and that goes as input to the hidden layer. And I also say that I'm going to start the sequence here, that is the starting a sentence here, right? So in this example, the caption is something like, young person drawing face on the sheet. Okay. So what is the first word to be generated? Young. Okay. So during training I say that the word to be generated at time 1 is young. Okay. And once it generates that word, that goes again as input to the hidden layer, right? And that takes the output of the hidden layer from the previous time instant, and also this additional input saying that I have generated this first word, young, then it needs to generate the next word. In this case, the next word is person. Okay. So this continues until we reach the end of the sequence, right? As you can see here, when I come up with the last word here, the next output is going to be end of the sequence. Okay. And this number of words in a sentence can vary from one sentence to another sentence, right? And we are going to look at the generation of the output of this model until we reach this end of the sequence. And how do we represent this verse itself was one of the questions that was being asked, right? Because anything that goes as input to the model has to be a feature vector. Okay? Like we talked about representing an image by a feature vector, we also have to represent the words by a feature vector. There are many methods that are being explored how to represent the words. One of these methods, commonly used methods, is what is called the word to vec. Okay? That is another model that has been trained to capture the relations between the different words that typically occur in a sentence, and then come up with a feature vector that contains the content of that word or some kind of relation of that word with the other words in the vocabulary of a language. Okay? So there is a method called the word to vec. There is also a method called the glow, which are very commonly used. There is also what is called a fast text. Okay? Any of these methods can be used to generate a feature vector to represent a word. That feature vector is the one that goes as the input to the model at every time instant. Okay? So basically this LSTM model or any recurrent neural network is trained to generate a sequence of words, right? And what sequence of words to be generated depends on the content of the image, right? During the training process, we have both of these. We have the image, we have the sentence to be generated. So we make use of both of these and then train the whole model, right? That's both the CNN model as well as the recurrent neural network model. And after the model is trained, then when we give a new image as input, right, it is supposed to generate that sequence, right? So we have moved away from the standard classification problems to the problem that take an image as input and then generates sentence as the output. That's where this recurrent neural networks play very important role. One can do many of these tasks like what we talked about, dense captioning and so on. And even the visual question answering also can be done by using this kind of a structure. Even the common sense reasoning can be done by the structure. I'll just show you how we can do that. And though these LSTMs were quite successful and better than the standard recurrent neural network, but unfortunately the number of parameters in those models is large, and also the time it takes to train the models is also very large, and also there is not much of scope for parallelizing the operations. Okay? So in 2017, another model was proposed which has kind of changed the complete landscape of these deep learning models. These are what are called the transformer models. Okay? As you've seen quickly, these transformer models are based on only the transformations. Okay? I'm not sure how many of people understand the term called the transformation. Okay? Let's look at a simple thing. Suppose I have vector x. Okay? Let's say it's some d-dimensional vector. Then I multiply this vector by some n cross d matrix. Right? You have n cross d matrix. You are multiplying that with the d cross 1 vector. What will be the output? It will be an n cross 1 vector. So you have some representation in the form of x. Then you are using some matrix. You are multiplying this vector x with this matrix. Then you will get a new feature vector. So basically you are doing some kind of a transformation. Right? As we are seeing later, this kind of a transformation is used several times and multiple transformations, right, in order to perform the tasks that we are interested in. And because this whole model is based on only the transformations, that model is what is called the transformer model. And these transformer models are mainly designed for what is called the sequence to sequence mapping task. I'll show you some examples. But interestingly, we are making use of these transformer models for the tasks like the image captioning, image question answering, and so on. So there are many text processing tasks where we deal with the sequences, right? It can be something like a simple sentence classification, right? I'm not sure you heard about the term called the sentiment analysis, right? See, nowadays we get feedback about a product or about a movie, right, from the users on the social media, right? It may be in the form of tweets or messages, right? Now you want to classify whether that message is a positive or negative, or whether the feedback is positive or negative, right? So we call this task as the sentiment analysis, where we have a sentence, not necessarily well-formed sentence, right? And the number of words in the sentence can vary from one sentence to another sentence. Now the task in the sentiment analysis is, given a sentence, you want to say whether it's a positive sentiment or a negative sentiment. Or you want to do what is called the parts of speech tagging. All of us know what are the parts of speech. Like we have the parts of speech like noun, verb, adjective, and so on. Given a sentence, we need to identify which words are nouns, which words are verbs, which words are adjectives, and so on. Again, the input is a sentence, the output is the different parts of speech associated with the words in the sentence. And similarly, there are what are called the named entity recognition. And very challenging task is the machine translation, where we have text to text translation. Typically, we have text in one language as the input. This is called the source language. And we want to translate that sentence in one source language to a sentence in another language called the target language, right? And typically, the translated sentence need not be having the same number of words as in the source language sentence, right? So what are we required to do here? We take one sentence as the input and generate another sentence as the output. The lengths of the sequences will be different. So we are mapping one sequence to another sequence. So that's why it's called a sequence to sequence mapping task. As you'll see later, we will pose my image classification task or the image captioning task as a sequence to sequence mapping problem, and then use these transformer models to perform this task. There is also an interesting task called the text summarization. That is, all of you write abstracts for your papers, right? What is it you try to do there? You summarize whatever is there in the paper in a paragraph, right? Same way, here we talk about given a text, maybe about a page or 2 pages, right? I want a machine or I want a system which can generate the summary for this input text, okay? And what is the text? It's a sequence of number of sentences, where each sentence is again sequence of words, right? And the summary is also a number of sentences, right? Again, each sentence is a sequence of words. So again, you can see that it's a sentence to sentence mapping or a sequence to sequence mapping. Only thing is, input is typically a much longer sequence compared to the output sequence here. And we can also consider the problems like textual question answering, where question is a sentence, answer can also be a word or a sentence. It's an open-ended question answering, right? So here also, if I have the training data where I have the questions and the corresponding answers for them, right? Now we train the model. After the model is trained, if I give a new question as input to the system, I want the system to come up with the answer for that, right? So these are all what are called the textual processing tasks, which involves mainly the sequence processing. So the task like this machine translation. Now let's look at the video captioning task. What is the input to the video captioning task? A video, right? What is the video itself? It's a sequence of frames. The number of frames can vary from one video clip to another video clip, right? So it's also a sequence, and it's a varying length sequence in the sense that 2 videos of the same domain can have different number of frames depending on the duration of the video. Now, what is it I want to do in the video captioning task? Given a video, I want to generate a paragraph that describes the content of the video, right? So now I pose it as a problem where the input is a sequence of frames, the output is a sequence of words, right? So once we map it as a sequence to sequence mapping task, I can try to use the models that are developed for the text processing. And each of these tasks involve mapping some input sequence to an output sequence. And in principle, one can use the recurrent neural networks to do this task, right? It also follows this encoder-decoder paradigm, but the encoder will take the input sentence, then it generates some kind of a representation of the sentence. Basically, we take the output of the hidden layer of the recurrent neural network at the final instant of time. Let's say the input sentence has got 10 words, right? After the 10th word, I take the output of the hidden layer that captures the representation of the complete sentence because it has looked at all the words in the input sentence. Now that representation of the input sentence is given as input to another recurrent neural network, which can be trained to generate another sentence. So in the case of the translation task, what is the input? Let's say I'm talking about English to Hindi translation. I'll be giving a sentence in English as the input. So the first recurrent neural network will capture the representation of that, and that representation will go as input to the second RNN, and that second RNN is trained to generate a sentence in the Hindi language. Okay? So now we can see that the same encoder-decoder paradigm which we looked at earlier, we use the different models in the encoder and decoder stages, right, to perform this sequence to sequence mapping task. So one can use the standard RNN or an LSTM to do this task, but as I was telling, typically the training times are much larger, the number of parameters is much larger, and also the scope for parallelization of the operations is not very high. Okay, so that's where we are going to see how to overcome these limitations, right, of the conventional methods to by using these what are called the transformer models. So basically, these transformer models are what are called the attention-based models. Okay, actually, the paper that was published in 2017 has got a very short title, right? But this is the most extensively referred paper nowadays in the deep learning domain, right? I think it's a few hundreds of millions citations for this paper. It's only a 4-page or 5-page paper, right? But it has provided a completely new paradigm for solving many of the problems. And the title of the paper is interestingly, "Attention is all you need." Okay. Now, what is this attention we are talking about? Okay. In the context of these transformer models, this attention refers to the relation between the elements in the sequence. All right. Let's say if you take a sentence, which is a sequence, there are different words, right? Now we want to capture the relation between the different pairs of words in the given sentence, right? Where I want to know how close are the given pair of words in a given sentence, right? What do you mean by close? They must be semantically close, right? Like typically a verb is associated with a noun, right? An adjective is associated with the noun, okay? So basically we try to capture these relations among the different words in the given sentence, and that capturing relation is what is referred to as the attention. And there are two types of attention. One is called the self-attention, other one is what is called the cross-attention. Self-attention talks about capturing the relations among the words in a one sentence, right? Whereas the cross-attention is capturing the relation between a word in one sentence with a word in another sentence. Okay? So basically, we'll be seeing that we'll be having two self-attention methods. One is capturing the relations among the elements in the input sequence, and that's a self-attention. And another one is capturing the relations among the elements in the output sequence. That's also self-attention. And the third one is what is called the cross-attention, where we take elements in the input sequence and the elements in the output sequence. Then we try to capture the relations across the elements in the two sequences. That's what is called the cross attention. And this is this figure that will come across whenever you try to look at this paper, right? And it looks little complex, right? But when you go through the details, we'll see that it's a very powerful model. Again, this also has got two modules. One is what is called the encoder module, and another one is what is called the decoder module. And encoder module itself has got what are called the number of layers, like we had number of layers in the standard feed-forward neural network. Here also there are multiple layers in the encoder, that's typically some n, and there are multiple layers in the decoder, that's also some n. But what is done within the layer of the encoder is two steps. One is using what is called the multi-head attention, and another one is using a standard feed-forward neural network. Okay, and this multi-head attention performs what we refer to as the transformations, but they are all linear transformations. When do we call a transformation as a linear? Let's say if I have vector x that's multiplied by the matrix M, where matrix elements are all some numbers, right? Then we are generating some y, which is M multiplied by x, right? So every element of y is related to elements of x in a linear way, right? So that's why we call it as a linear transformation. As we'll be seeing later, right, we perform this kind of a multiplication, multiple such transformations that we'll be doing. That's why it's called the multi-head attention. Each head corresponds to one type of transformation that we do. So typically we use this multi-head attention that takes as input the sequence, right? It can be sequence of words or sequence of frames in a video and so on, right? And then it captures the relationship between the elements of a sequence, and that generates a new sequence. And if the model is completely linear, that's not going to be powerful, okay? So we have to bring in the nonlinearity. That nonlinearity is provided by this feed-forward model, which is standard feed-forward neural network that we have seen. What are the hidden layers that we use in the feed-forward neural network? Typically they use the sigmoidal activation functions or ReLU, which are nonlinear activation functions, right? So they bring in the nonlinearity. And this encoder takes an input sentence and then generates a new sentence as the output of the model. And similarly, the decoder, let's say if it's going to be used for the translation task, right? I'll have, let's say it's a translation from English to Hindi, I'll have English sentence being processed by the encoder. I also have to capture the relations among the words in the Hindi sentence. So the decoder model will first take the target sentence and then captures the relationship among the elements of that Hindi sentence. That's why you can see that there is a multi-head attention here also. And here also we get a representation of this Hindi sentence. Now I need to relate the representation of the English sentence and the representation of the Hindi sentence. That we do by one more type of attention. This is a cross attention here. Okay. So here we do self-attention for the input sentence. Here we do self-attention for the target sentence. Once we get the representations of the input and the target sentence, we capture the relations among these two representations by using the cross attention here, and then we finally generate the output of this model, which is supposed to be the target language sentence. Okay, that's how we need to look at this structure for the task that we want to perform. Okay, now let's try to understand what is this attention, how it can capture the relations. There's a little bit of math involved. Okay, I hope it's fine with you. Basically, what we use is what is called the scaled dot product attention in all these models. And the terminology for this scaled dot product attention is derived from what is known as the linear regression method. That's one of the machine learning tasks. I'll put it in a very simple way. I have some desired output yn for input xn. Like that I have n number of inputs. Okay. Now for a new x, I want to predict what is the y. Okay. So now the query is x here, right? And I have the prediction values y for each of these xn's, right? Now each of these xn is what is called the key, and each of these yn is what is called the value. Okay? So basically for any given query x, I generate this output y, prediction output y, as a combination of the relation between the query and key, which is multiplied by this value for the xn. Okay? I just want you to note that there are three terms called the query, key and value, and as we see quickly, these are the three entities that will be dealing extensively in these transformer models when we perform this attention task. Okay. So basically, the scale dot product attention deals with these three different entities, what is called the query vector, key vector and the value vector, and each of these is derived from the elements in the sequence. Okay. Let's say the length of the sequence is this capital 10 T is 10, right? When small t equal to 1, we are referring to the first word. When we are referring to the second word, this small t is equal to 2 and so on, right? And for each of the words, we have some representation in the form of the x, right? And what we'll be seeing little later is we generate this query, key and the value vectors from that x representation by doing the transformations, right? And then we want to capture the relations between these three entities. Okay? And as all of you are talking about the cosine similarity in the morning, how do you compare the cosine similarity between two vectors? Yeah, you compare the dot product between two vectors divided by the product of the norms of the two vectors, right? So basically dot product is a measure of similarity, right? So here we use dot product based similarity, right? So this symbol here, angular brackets, right, between two vectors, right, is what is basically measure of similarity that's indicated by the dot product. So basically I compare the dot product between one query vector, that's qt, and one key vector, that is the km. Okay? And the result of this dot product is what I refer to as the alpha tm. So what does this give us? I have a word at time t, I have a word at time m, right? And I have the query representation of that word at time t, and I have the key representation of that word at time m. Now I want to see how similar they are. Okay? So one way of capturing the similarity is by computing the dot product, and where the scale comes in, we are dividing the dot product by square root of d, where d is the dimensionality of all these vectors, right? So that because the dimensionality vectors can change from one type of data that you are dealing with to another type of data, right? And you want the dot product to be independent of the dimensionality, right? So that's where this term called the dot product and scaling comes. So this alpha tm is actually nothing but the scaled dot product between two entities, qt and k. And using this scale dot product, we compute what is called the attention score, that gives some kind of a representation of the similarity between this qt and km. Okay, or yeah, okay. So you can see that what is it I'm doing here? All of you are, I think, familiar with what is called softmax operation in neural networks, right? When you want the outputs of all the neurons in the final layer of a classification model to add up to 1, right? Then you use this softmax function, right? So basically this softmax function will guarantee that the result of the applying the softmax operation will give us values in the range 0 to 1, right? And the softmax is given by this function e power alpha tm summation e power alpha tj, j equal to 1 to capital T, right? So basically you are changing this m here from 1 to t, and then computing this expression that gives us some kind of a score in the range of 0 to 1, right, to represent the relation between the query vector and the key vector, right, at time t and m respectively. Okay? This is what is referred to as the attention score, right? Now we do a very important operation to generate what is called a context vector CT for every QT. Okay? What is it we do in this?
generation of the CT, we can see that CT is expressed as summation alpha Tm multiplied by Vm. Vm is the representation of the word M using the value vector form, and that's multiplied by this attention score, right? Then we do this summation over all words that we'll have in the sequence, right? So basically, when you multiply a vector by a number, it will also be a vector. Then you're adding all these vectors to get another vector. So finally, what you're getting is a new vector. But what does this new vector contain? It captures the similarity of a particular word at time t with all the other words in the given sentence, and we make use of these relations between the given word and all the other words to generate a new representation of this word, right? So basically this context vector is a new representation of the query vector, which is again a representation of the word at time t. Okay? So with this we do it for every word in the sentence, which means that I'll get the CT, right, by performing this operation for every word in the given sentence. When I do this, I get a new representation of the complete sentence, which is also going to be a sequence of vectors of exactly the same length as capital T, right? But the representation is different from what we had originally. Okay? But how is this representation captured? This is related to how a particular word in this sentence is related to other words in the same sentence. It's a self-attention mechanism, right? And the whole operations here is what is referred to as the scale dot product attention, which takes the representation of one word and all the key vectors and all the value vectors, and it then generates this context vector. And this collection of all these key vectors and the value vectors are what are called the K and V matrices, right? And where these vectors are nothing but the columns of these matrices. So basically what we are doing is we are getting a new representation of this word at time t in the form of this CT. Okay? But as we were saying quickly, right, this dot product is a linear operation, and the way these query vectors are generated, or the key vectors and value vectors are generated, are also by performing certain transformations. All of them are also linear operations. Okay. Now we introduce this term called the single head attention, which tells us how we generate this query, key and the value vectors from one of the elements in the sequence, right? Let's say if I take x1, I multiply that x1 with this WQ matrix, I'll get some new representation of that word. Similarly, I multiply this vector x with another weight matrix, right? That gives us a key vector. Similarly, this x is multiplied by another vector w, another matrix w to get this value vector, right? So we have three different matrices applied on the same vector. When the matrices are different, right, the output vectors are going to be different, right? And therefore we get some new representations of this xt, right? On that we perform this scale dot product attention, and that will help us to generate a new representation of this xt, first generated to qt, and from qt we get this ct. Okay? And the collection of all these wq, wk and wv is what is called a single head, because we are using all of this on the input to generate this key, value and the query vector representations, right? And all this collection of these three matrices put together is referred to as the single head attention. And as you can guess, when I change these matrices, right, the transformations will be different. So I perform multiple such transformations to generate multiple different representations, and then capture the relations among the words, and then generate these context vectors, right? So when you say single head attention, we are generating the context vector from the elements in the input sequence using one set of these transformation matrices. All of this refers to a single head, all right? And when we talk about multiple heads, now we bring in index associated with the head here, right? You can see that earlier we had simply WQ, right? Here we have WIQ, where I refers to the head index. like typically the number of heads is 4 or 8 in a transformer models, right? So if there are 4 heads, then I'm going to have 4 different sets of these matrices, right? That will give us 4 different sets of transformations that are used to generate this query key and the value vectors. Once these vectors are changed, the CT vectors that you get will be different, right? So that's why for every head you get one C vector, right? And typically the dimensions of this will be related to the original dimension and the number of heads. H is the number of heads, and typically the dimensionality of this context vectors is given by L, that's equal to D by H. D is the original dimensionality of X, H is the number of heads. Let's say D is 512, right? If you are using 4 heads, then this L dimension is 128. The reason is that once we get these CITs for the multiple heads, and when you put them together, again it comes back to the same dimension as the original input, right? That's why we finally take these CITs for the different heads and then concatenate them together to get one representation of each of the words in the given sequence. That's finally represented by this CT tilde, right? And there's one more linear transformation that's normally performed to generate a new representation. So the output of this multi-head attention, right, is a new representation of the given sequence. The given sequence is x1, x2, so on, x capital T, and finally we generate z1, z2, so on, z capital T. But how are these jets generated? These jets are generated by performing operations using the multiple heads, where in each head we perform linear transformations to generate the query key and the value vectors, and then we combine the information about the similarities between the words and the value vectors to generate these context vectors, and from the context vectors we derive these z vectors. Basically what we are trying to do is, given a sequence, right, we get another new sequence, right, but this new sequence is supposed to capture the representation of the relations among the different elements in the given sequence, and that forms the most crucial part of the transformer models. But all of this is only linear operations. Okay, this is the pictorial way of telling you what we have done. So we take the word at xt, right, and we pass it through all the heads, and in each head it is multiplied by the different matrices, right, to generate this query key and the value vectors. Then we perform the scale dot product attention. Then we generate this context vector. This we do it using each of the multiple heads, and once we get these context vector representations, we concatenate them and then perform one more transformation to generate this zt. So for every element in the sequence x at time t, we generate the new representation zt, and what is done in the feed forward neural network is bringing in the non-linearity, right? So we said that we take this z corresponding to a feature vector, then we pass it through this feed forward neural network. This is a standard feed forward neural network. As you can see here, there is input layer, non-linear hidden layer, and the output layer. So from this z1, we generate a new output called the x1 tilde, which is related to this z in a non-linear way. So basically this x1 tilde is the new representation of the x1, x2 tilde is the new representation of x2, and so on, okay. But all of this forms only one layer in the encoder module, okay. So once we get this representation from the first layer, the output of the first layer goes as input to the second layer, which has got exactly the same structure, same parameters, right, except that inputs are changing, okay. So basically all of this forms one layer, like you can see here, there is a self attention, multi-head attention, then this feed forward neural network. So this forms one layer which takes the input sequence and then generates a new sequence, and this we do for multiple layers in the encoder module. Like you can see, the input sequence is given here, then we generate the new representation x1 tilde. That x1 tilde goes as input to the second layer, then we generate x2 tilde, and so on. If there are L layers, then I get the final output here. This what is supposed to capture the relations that are there in the words elements in the sequence, but we are getting some new representations of the input, and the new representation is non-linearly related to the original sequence. Okay. Now, where is the scope for parallelism here? Can I do all these operations for the different inputs simultaneously? Right, like what we said here. Yeah, I am taking entity at time 1 and then do all the processing, right? I take the entity at time 2 and then do all the processing, right? So basically we can do the processing for all the entities in the given sequence simultaneously, right? That's where it provides the scope for parallelism, and also these multiple heads can be done simultaneously, right? That's where these transformer models have lot of scope for parallelism operations, and typically these are all run on the GPU structures, right, where you can parallelize the operations significantly so that the time taken to train the model can be significantly reduced. Okay. Any questions? So basically what we looked at is how this encoder module in the transformer model is like and what it does. So important thing to note is that I give this original sequence as input, then pass it through several layers and then generate a new representation of that sequence, but the sequence length is exactly same as what we have. Okay. And this is supposed to be a new representation of the input sentence. And what is it we want to do in the decoder? We want to do a similar thing for the target language sentence, right? So that's why we do this self-attention, again the multi-head attention. So we get a new representation of this. Now we need to relate the target language sentence and the source language sentence. So we take the output of the encoder module for the source language sentence and then take the representation of this target language sentence. Then we perform this cross attention, multiple head attention, similar to what we have done, so that we combine the information that's present about the words in the input sentence and the words in the target language sentence, right, and then get a new representation of this both the inputs, and that also is a stack of layers. And once we have this stack of layers processing this input, right, then we pass it through another linear layer and softmax layer to generate the probabilities for the different words, right, and we use this to decide on which word has to be generated at time t. Okay. So basically the decoder generates one word at a time, and the sequence of that words put together is the sentence that's generated by the decoder module of the transformer. So basically in the training of this model, we have the target language sentence for every source language sentence. We use both of them to train the model. During testing phase, obviously we don't have the target language sentence, we only have the input language sentence, right, and the model should take the representation of the input language sentence and then generate, yeah. Yeah. No. Here the query is not same as what we talked about query in the retrieval task, right? As I said, here I want to come up with the relations between the query key and the value, right? So basically we generate this query key and value from the same entity, okay? And the output of this multiplication operation is what is called as the query vector, right? And I want to generate a new vector for this Q, which is called the context vector, right? And that is done by looking at how similar are these query vectors with respect to key vectors, right? So the attention score is computed by matching the query vector and the key vector. Once I get the attention score, I use that attention score to multiply the value vector, right? And a combination of these value vectors with the different attention scores is what gives me a new representation of this query vector, right? So here the query vector is used from the sense of the function approximation task I was talking about here, right? It is not the query word of the image retrieval, right? So every word in the sentence becomes a input for generation of the query key and the value vectors. Yeah. Okay. I know that it's a little intense. Okay. Basically, what I wanted to note is that what we are doing is, given a sentence, right, where we represent the sentence in terms of whatever that word to vector, below feature vectors, right, we pass it through this encoder module to generate a completely new representation, where that new representation captures the relations among the elements in the sequence, and then also performs the linear operations and the nonlinear operations, multiple linear operations through the multiple heads, right, and we get a completely new representation for this input sequence, which is supposed to be capturing the relations among the different entities in the input sequence, right, and that's what is used for generation of the target language sentence if it's a machine translation task. Okay. Right. Okay. Now we will be seeing so if you have any sentence to sentence mapping tasks, one can use the transformer models, right? But interestingly, these transformer models are also extensively being used for many tasks like image classification, image captioning, and so on. Okay. So when I talk about image classification using the transformer model, right, we refer to it as the vision transformer, right? But this transformer models requires a sequence as the input. So how do you generate a sequence from an image? Okay. I mean, this is not a very natural way of doing it, but it's a fairly meaningful. So what is done is, I take an image, I divide that into multiple parts, right? Like in this case, I am dividing that into 9 parts, right? Then I am putting those parts in a particular order, right? Now I take each part here and then generate a feature vector for that, and for these 9 parts here, I'll get 9 feature vectors, right? That forms as the input sequence to the transformer encoder module, and it will do all these transformer encoder operations. It generates a new representation, and that new representation goes as input to the standard multilayer feed-forward neural network, which can be used to perform the classification task, right? Why is it called the vision transformer? Because the input to the transformer module is the representation of the image as a sequence, right? And what we are doing is, we are not using the decoder here, as you can see, right? Because once I get the new representation of this input sequence, I use that new representation to perform the classification task, right? This is what is called the vision transformer. There are other types of transformers. I'll just leave here. Now let's see how we can do this image captioning task, right, using the transformer. Earlier, how did we do? We had 2 modules. One is the CNN model, which takes the image as input and then generates a representation that goes as input to a recurrent neural network, right? But here we can see that I use a transformer model, but it uses the vision transformer. Now again, I take the image, divide that into parts, and then generate a sequence, and that sequence goes as input to the encoder module of the transformer. And here I have a sentence to be generated as the output, like in the translation case, right? So now the decoder model takes this representation from the encoder and performs the generation of the sentence, so that what I get here is the caption for the given image, right? So the main advantage is, again, instead of using a RNN model or an LSTM model, I can use the transformer model, where I can parallelize several operations, but I pose it as a sequence to sequence mapping task and then carry out this image captioning task. Actually, these are some of the results of some work done by one of my MTech students, where we developed a system for generating captions in one of the Indian languages, that's Telugu, right? I mean, if you are able to read Telugu sentence, then you'll be able to see that, right? So basically, what is shown here is the images and the sentences that are given by the humans, right? And what is shown below is the sentence that's generated by the captioning system, right? And as you can see here, the captions will not be exactly the same as the caption given by the humans, but they are very similar. The number of words also can change from the actual prediction, right? But it gives a fairly good output as a caption for a given image, but the caption is generated in the Telugu language. Like this you can do for any of the languages. And there are number of papers available where I want to generate a very detailed caption from a given image, which is called the image paragraph captioning. Again, we use the VIT encoder, that's the vision transformer encoder, which takes the image as input and then generates a representation of that image as a sequence. Then we have this transformer decoder, which generates the caption for that sentence. As you can see here, the ground truth caption has had only 4 or 5 sentences, right? But the system generated caption has a much more detailed description of the content of the image. As you can see, there are about 10 sentences, right? Because this is given by one of the humans, right? So that person might have been very brief in giving the description, whereas the system which has been trained to generate the captions generates a much more detailed caption generation, right? And there are a number of papers which talk about how to generate this kind of paragraph captions from the given image. And this is again one of the works done by my PhD students, where we do this video captioning task again using the transformer models, and this is called a multi-modal attention based transformer, where we give the video as input, then we extract different kinds of information from the video, like we identify what are called the keyframes and the objects, then some kind of a semantic representation, and give all these 3 as input to the encoder module, and the output of this encoder model goes as input to the decoder module. Then it generates a sentence that gives a caption for the given video. Again, the details are available in this. Similarly, one can do what is called the dense video captioning. There are some papers related to that. I'll skip that. And there is also some work done on how to reduce the number of heads, because as the number of heads increases, the number of parameters is much larger, right? So there is a model called the deep and lightweight transformer, shortly called as the delight, which says that one can use a single head to perform the task, okay? And again, there are some papers available on that. There has been work done on machine translation using this delight transformer. Okay. Now we come back to our original problem that we had, right? So all training of these transformer models has to be done in a supervised manner, right? Why? Because if you are talking about machine translation task, you must have, right, the source language sentence and the corresponding target language sentence. And if you have only these pairs of sentences, then you can train the complete model, right? Again, as you can see, the number of parameters is fairly large, right? Because the number of heads and the size of the transformation matrix, all of this decides the number of parameters. And if the number of parameters is large, again you require a large number of labeled, or in the sense the examples where you have the desired output specified, right? So in order to address this problem of finding the adequate number of supervised learning examples, here also we address how we can do pre-training in a unsupervised manner, right? So that we can take this pre-trained model and then build the complete system, right? So there is a lot of work done on how to perform the pre-training of these transformer models. Some of the most popular ones are what are called the BERT models, which stands for the bidirectional encoder representation from the transformer. I will briefly describe that. This basically is trained on the text data, right? But it takes data from only one source domain. Yeah, like typically it's done for the English text, right? So I take a large number of sentences in English text, right? There's nothing like what is the desired output for them, right? I use a number of such sentences in English and then train only the encoder part, right? It's called the bidirectional encoder because we are looking at the relations between the words irrespective of where that words are positioned. Okay. Whereas another one is the more very popular one, right? What is called the GPT model, right? Generative pre-trained transformer, right? I think all of you are aware of what is called the Chat GPT, right? And Chat GPT is built using this GPT model. This GPT model is also a pre-trained model, but it's a unidirectional model. Basically, it tries to capture the relation between a word and all the words prior to that, right? That's why it's called the unidirectional model, but it has been shown to be very powerful. And in both this BERT model and also the GPT model, we are talking about only the text data. But if we want to build a model for the tasks like visual captioning, then we need a pre-trained model not only for the text data but also for the visual data, right? So there is also a variation of this BERT model called the Vision Language BERT, which is a pre-trained model on both the image and the text data. This is called the Wilbert model. So basically what is done in the BERT model, which is a pre-trained model for the text data, is basically train the model to generate a representation for many natural language processing tasks that you want to do, right? There are two training methods for this pre-training, but both of them are unsupervised training. One is what is called the masked language modeling and another one is the next sentence prediction model. Let me briefly explain that. Suppose I have a sentence, okay? It's an unlabeled sentence, right? Then what we do is we mask a few words in the sentence, okay? Then we train the model to predict these masked words in the output of the model. So this doesn't require any desired output of the sentence, right? It only takes the word, takes the sentence, then it selectively masks a few words in that sentence, and this masked sentence goes as input to the model, but at the output of the model, I try to predict all the words in the given sentence, okay? This is what is called the masked language modeling. The next one is, you take a text, if the text has got several sentences, right? You take two consecutive sentences, then say that if I give the first sentence, the output of the model should be the second sentence, right? That's why it's called the sentences A and B, okay? So I give both these sentences and I want the system output also to generate the second sentence from the first sentence, okay? Again, there is nothing like a desired output, right? Like in the translation task, I just take every pair of sentences in the given text, right? And then I want the system to predict the second sentence from the first sentence, right? So all of this can be done using huge amounts of text that's available, right? So that we can estimate the parameters of the model, right? And once we have the estimation of the parameters of the model done, then we can do fine tuning for any downstream task. The downstream tasks are like you may want to do the textual question answering or translation or sentence classification or any of these, right? But you may have only limited amount of data available for this, right? So what you do is you take the pre-trained model, then fine tune it for the given task, right? And then build the system for the final downstream task. So this using this pre-trained models has become very common nowadays, right? Mainly because you need to build a complex model, but you may not have sufficiently large number of training examples, right? So you take a pre-trained model and then do only fine tuning for the task that you are interested in. Yeah, same thing that I was talking about. And as I said, one can also talk about these BERT models for a combination of the visual data and the language data. So basically, we take the representation of an image as a sequence of parts, or if it's a video, it's a sequence of frames. So I get one sequence here, then I have the corresponding sentence associated with this, right? And then I use both these inputs to come up with some common representation, right? And that's done by using the transformer models, right? And this model is what is called the vision and language BERT model. Once we design it for some data, right? Then if you want to use it for any task of your interest, then again you can do the fine tuning and then go ahead and build that model. Okay. And similarly, this GPT model, as I said, the difference is that in the GPT model, it's a unidirectional prediction, right? But it also performs similar operations like that. And here also we perform the pre-training using the text data where there is no desired output, right? And once this decoder is trained, then it is trained to predict any new sentence, right? And typically this GPT model is used in the decoder stage. Okay. So coming back to the task that we were addressing in the beginning of the sessions. Now if I want to solve these problems like visual question answering, right, or common sense reasoning, if you remember, the visual question answering involves given an image and given a question, we need the model to come up with the answer, right? It can be one of a fixed number of options. Or yeah, how can you solve this problem? I have one image encoder module which gives the representation of the image, right? And we have another encoder which takes the question, and we get the representation of the image, representation of the question. Then we combine these two representations typically by again using the attention mechanism. And once we get the common representation of both the image and the question, then I have a module that can generate the answer. If it is a multiple choice type questions, then it will be a classification task. If it is a open-ended question answering, then this module will also be capable of generating a sentence. Okay. So basically we use combination of different neural network models, like image encoder can be CNN or a visual transformer, and the question encoder is typically an RNN model or the transformer encoder or BERT model with the fine-tuned one. Then the fusion of the representations can be just a concatenation of these two, or we perform what is called the capturing the attention between the two representations, that's called the co-attention. Then answer generation, as I said, it can be a simple classifier if it's a multiple choice type question, or it's capable of generating text like the GPT, right, if it's a open-ended question answering system. So one such system that has been developed for the visual question answering for the images is what is given in this paper, right? As you can see here, I take a CNN to represent the image. I use a recurrent neural network like the LSTM to get the representation of text. I concatenate the outputs of these two models. Then it goes as input to another recurrent neural network to generate the answer for the given question and the given image. Or I can also use these BERT models where I take the image and the question and give both of them as input to this Wilbert model, and then it generates a representation of both the image and the question. Then that representation goes as input to the answer generator module, right? So this basically uses the Wilbert model to perform these tasks. Yeah. What is this open-ended VQA? There are no multiple choice questions, right? The system has to come up with a sentence that corresponds to the answer for a question. Like in this case, I am giving this image, then I am asking what is the zebra doing, right? In the multiple choice type questions, let's say I give two options, eating or grazing, right? The correct answer is grazing, okay? But a open-ended question can be, I ask the system to generate a sentence about what the zebra is doing, so the system has to generate the sentence like the zebra is grazing in the grasslands. Open-ended is always a sentence, right? Or it can be a word also, but I am not giving the multiple choices for the word, right? Yeah. So this is another example. What is the dog's? What is in the dog's mouth? So one can simply say it's a toy or a purple toy, right? But if it's an open-ended VQA, then you typically give a full sentence saying that the dog is playing with the toy in its mouth. Okay. So it all is a question of what type of answers you are expecting for the question. And if it's an open-ended VQA, then the final module here is going to be different, right? Because it requires a sentence to be generated, and typically it generates one word at a time. So the words that are generated up to some point of time go back as input to the model, right? So that we make use of that information to predict what is the next word, right? So typically the open-ended VQA will have this kind of a structure. This structure is more or less similar to what we had earlier, right? But we need this additional module here to generate a sentence, right, one by one word at a time. Okay, yeah, this is whatever we talked about for the images, one can also do for the video. Again, we need some representation of the video, and we have the representation of the text. Then we combine them and then generate the answers. Again, there are a number of papers on that, and there is also interesting work that's being done where I take the output of a captioning system and make use of the caption also to generate the answers. This is what is called the caption guided visual question answering. As you can see here, I have the image, I have the question, then I pass this image to a caption generator and then generate the caption, because the caption will have some information about the content of the image that can be helpful in answering the question, right? So we get the caption from the caption system, then take these three inputs and then come up with the answer for the question. So basically I need to relate what is there in the image to the question, and the question to the caption, and the image to the caption, and we combine all these different pairs of representations and then fuse all these representations, and then we finally generate the answer. So many cases it has been shown that using this caption will give you a better performance in the question answering task. Okay, and the most challenging task is coming up with the reason as well as the answer, right? Again, we have explained this earlier. Okay, so there are a few subtasks here. The input is image or video, then there is a question, then answer needs to be generated, and a rationale or the reason needs to be generated. So the subtasks are how to come up with an answer for the question, then given both the question and the particular answer, what is the reason for selecting that answer. But finally, what I want is, given a question, coming up with the answer as well as the reasoning for that answer, right? So these are the different types of subtasks involved, and these answers can be multiple choice type, and similarly the rationale can be multiple choice type, or it can be open-ended, right? And accordingly the complexity will be different. So people are addressing all these problems, and again the most common paper is what is called the recognition to cognition. What do you mean by this? Typically, when you perform classification, we are only recognizing what is there in the object. But when you are talking about all this question answering and common sense reasoning, right, it's a cognitive task, right? So the title of this paper is what is called From Recognition to Cognition, which involves visual common sense reasoning. As you can see here, I take the image and then give it a CNN to get the representation of the image. Then the questions and the answers are passed through this BERT model, and then we combine these representations and then try to come up with the answer as well as the reason, again using the standard recurrent neural networks. But there is also a lot of work that's being done where these recurrent neural networks are replaced with the transformer models to perform these tasks. Okay, so these are the different details of that. Okay, maybe I'll skip that. Okay, any questions? Yeah. Yes, yes. Yeah, you can do that. Like what we have done for the image classification, we represent the image as a sequence, but I wanted to do only classification, right? What is done in the sentence classification? Again, I have a sentence. I have to decide what class it belongs to. So I give the sentence as input to the encoder of the transformer, then get a new representation of that. That new representation will go as input to the standard classification model. Then you perform classification task. Similarly, the parts of speech also. So basically, we use the encoder here to get a new representation of the input sentence, where that new representation captures the relations among the elements in the words, right? Yeah. Yeah. Not this one. Yeah. This is basically explanation of whatever I mentioned here, right? So basically, in the performing this visual common sense reasoning task, there are three tasks, what is called grounding, contextualization, and the reasoning. Okay, that's what is explained in the next slide here. When you say grounding, we need to learn a joint image and the language representation, because I have a image and I have the question, right? So I need to relate the content of the image to the query, and I also need to relate the content of the image to the answer, right? So capturing that relationship is what is called the grounding, okay? So it says that learning a joint image language representation for each word in the query or answer with the relevant objects in the image, okay? Once I do this grounding, then I have to relate the different words in the query with the different words in the sentence and also with the different objects in the image. That's what is done in the contextualization. And once we get the grounding and the contextualization done, then we come up with the results. Okay, any other questions? Maybe we'll spend a few minutes on very hot topic nowadays called as the generative AI. Sorry? No, I don't get your question. Mm-hmm. Yeah, you can do that. Okay. But what will be the text input in the case of captioning task? Sorry? But that is the desired output, right? When you, let's say you build a system, then for a new image, if you want to generate the caption, what will that input? Will not have that input, right? Yeah. So I can't use the Wilbert model for the image caption, because the Wilbert takes some image as the input and also some text as the input, right? Then only I can generate the representation of that. But during the testing of the image captioning task, I have only the image. I don't have any text there, right? So I can't feed it to the Wilbert model, right? Yeah.
Sir, most of the English transformer models,
Yeah.
any model for that matter, when it comes to text, as for English language.
But in principle, one can do it for many of the languages. Actually, there are many of our colleagues who are working on this. Okay. So basically, what you need is the representation of words. Like what we have the word to wake and glow for English, we need to come up with the representation for the words in the other languages. Once you come up with that, then you can use any of these models, right? It's only the generation of, yeah, basically need, let's say if you want to develop a system for Hindi, right? Hindi to English you want to develop, let's say translation, right? So then you need some representation of the words in Hindi, right? All this word to wake and the glow are trained using the English text data, right? So you need to build a similar model for the Hindi text. One of our colleagues, Dr. Mitesh Kapra, he is leading the huge project on what is called the AI for Bharat, right? So that's where they are focusing on translation from English to Indian languages or from one Indian language to another Indian language. He's also working on what is called a speech-to-speech translation. That is, given speech in one language, how do we generate the speech in another language? So he is exploring many of these transformer models for many of the tasks like this. And in the process, they are also developing these systems for generating the representations of the words in the Indian languages. Yes. Yeah, people are exploring different methods on how to deal with the low resource languages. Mainly they use these transfer learning techniques. Basically, let's say if you develop a system for Hindi language where there's a huge amount of data, now if you want to develop a system for Kannada language where let's say there's a limited amount of resources, right? So you take this model that's trained for Hindi, then kind of fine tune that, right, for the low resource language, or you do some kind of an adaptation on that, right? So that's another interesting research area where you have a system that's built for a high resource language, right? Then use that to develop the system for the low resource languages. Yeah. Right. Good. Any other questions? Okay. So let's try to understand what are these generative models. Okay. As the name itself indicates, we want the models to generate the data, right? Actually, all these LSTM models, the transformer decoders, and that we have seen, they're all capable of generating the sentences or the sequences, but they generate the text data, right? But there is a lot of interest nowadays in generating not only sentences, but other types of data, like you may want to generate the images, you may want to generate the speech, you may want to generate the music, or you may want to generate the videos, all right? What is the purpose of generation of this data, right? From the machine learning point of view, I can use it for the augmentation of the data, okay? So, I want to build the models that are capable of generation of data, where this generated data can be used for the augmentation of the data. And there are a number of models in the deep learning which are kind of capable of generating data. We don't study much about what is called this restricted Boltzmann machine, though that is the paper that has triggered this whole of deep learning research in 2006, okay? But it's a very complex model. That's why the people have kind of stopped using that model. But that's one of the first generative models. And we talked about autoencoders. There is a particular type of autoencoder called the variational autoencoder, which can also be used for generation of the data. As we have seen, the GPT model can be used to generate the data, text data. But what we'll be looking at is how to generate the other types of data, and that's where this very extensively used model called the GAN model comes to the picture, which is called the generative adversarial network, and it has been extensively used for generation of the images, okay? And one of the current topics in the past 2 to 3 years is what are called the diffusion models, which can be used to generate the image data or video data or audio data from a text input. So earlier we talked about given image, how to generate the text that describes the content of the image. Now I want the other thing to do. I specify a sentence which tells what should be there in the image, right? Now I want the system to generate an image that will have that content, right? And similarly, I want to generate a video that corresponds to text, or I want to generate audio or music or speech, right, that corresponds to the text, right? So, people are looking at how to do this different types of tasks. We'll briefly touch upon GAN and very briefly about the diffusion models. So, the typical structure of this GAN model, which can be used for the generation of the images, has got two entities. One is what is called the generator module, and another one is what is called the discriminator module. And interestingly, both this generator and discriminator are all CNN models, okay? It's a combination of two CNNs that are used to build this GAN model. So what we do is, we take the real images, okay, and then we take one of the images as input. Then we train, let's say, this model called the generator, which takes some random input, it's typically a random vector as input, and then it will be trained to generate an image, okay. And then I look at this real image and also the image is generated by this generator module, right, which is not a real image, right. Then I use a discriminator to tell me whether the input to this discriminator is a real image or a image that's generated by the generator. I don't want to use the fake because it's not really a fake, right, but it is not the original image, okay. And I want the discriminator to perform this task of discriminating between the real image and the generated images as well as possible. But what is it I want the generator to do? I want the generator to generate the images which are very close to the real images, okay. So both these models are combinedly trained, right, and once this model is completely trained, right, then I can take only this generator module and then give some random vector as input and then generate the images, okay. So why are we calling it as a adversarial network? Because for every real image, I want to generate an image from the generator module which is very close to it, right. So it's a kind of a competitor for that. Okay, that's the reason why it's called as the adversarial network. So basically, the generator is a CNN model, and the discriminator is also CNN model, but it has got only two classifier, because I need to tell whether it's a real image or a generated image. And one can train this model for generation of images in a particular domain, right? Because it involves training of the model using the real images in a particular domain. So typically, if you build a model for one domain, it has to be used to generate the images only in that domain. If you want to build a image generator system for a new domain, then again you need to retrain this system completely. Again, there are lots of details. I'm skipping the details. But there are a number of interesting applications of this GAN to perform some challenging tasks. Yeah, there are, see, typically when we talk about CNNs here, it's a two-dimensional CNN, where image is the input, right? If you give one-dimensional input to the CNN image, right, then we're talking about something like a text. Yeah. Both the generator and discriminator will take a one-dimensional input, yeah, but it's sequence. Yeah, yeah. So there are what are called the text GANs available. Now, suppose I have these images and I want to perform some changes in these images. What changes I want to perform are given by a sentence. Okay? Yeah. So let's take this first case here. I want to generate the images where the flower has petals that are white and has patches of yellow. Right? Now what is it you see in this set of figures here? Every figure here corresponds to original image. What is the difference between this and this here? All the petals are changed from what are the original color to white, and all the patches are changed to yellow. Right? So basically I want to do some kind of a generation of new images, but I am specifying how those new images should be with reference to some set of input images. If you look at the second one, the petals of the flower have yellow and red stripes. Okay. So again, we take every figure here, right? Then we change the petals in such a way that all the petals will have yellow color and the red stripes, right? This is what is called the text adaptive GAN. Why is it called text adaptive GAN? The text that we give as input here tells what changes we want to make in the given image, so that the new image will contain whatever the details that are specified by this caption. In the same way here, yeah. No, yeah, how to process this sentence, right? Again, I can use any of these sequential models or a one-dimensional CNN, right? Basically, I need to understand what this sentence says and then incorporate that suggested change in the image. Yes. Okay. So here is another example. I have the images of the birds. Now I want to say, I want to have the images with the blue crown and white belly, right? So basically, we change all the color of the crowns to blue, right? And all the bellies to white. Okay. So basically, we need to identify where the crown part is, where the belly part is, right? And then change only those parts, right, as guided by the text, right? So this is one of the interesting tasks that are done using the GANs. And another interesting task is go from one domain of images to another domain of the images, but they are somewhat related, right? Like here, I have, yeah, what are the animals that are present here in the top row? They are all supposed to be zebras, right? And what you are generating are the horses for them. Whereas here, I mean, if you look at it closely, right? Yeah, what do we have here? No, cat. Okay, and what we are generating are the dogs, right? But we want to have the features of the dogs having similar features of the cats, right? But I want to generate the dog images from the cat image and so on, right? So basically we are talking about performing the transformation from one set of images to another set of images. So there are some models that are being explored there. Okay, and there are varieties of these GAN models that are being explored. I'm just listing them. As you can see here, one of them is what is called the text GAN, right? And there is also a combination of these GAN models and the transformers called the GAN former, which can be used for variety of tasks, right? And there are a number of variations of these GAN models. And we have done some work on how to use this GAN model for the video captioning. Okay, maybe in the interest of time, I'll skip that. Yeah, we'll close with a brief discussion on what are called these diffusion models, mainly for the image generation. It's a very interesting approach, but there is a lot of strong theory that underlies that, and also it's a fairly complex technique. One of the types of diffusion models is what is called the denoising diffusion models. What is it you see in this picture? Yeah, okay. I wanted to focus on the picture here and the picture here. Two types of dogs, right? Yeah. So I'm giving the picture of the dog on the top as input to the model, and the model generates the picture in the bottom, right? Yeah, the system takes this picture as the input and it generates this picture as the output. So basically I'm getting a new picture of a dog which is obtained from one picture of the dog. Okay? What is interesting here is we make use of noise in a purposeful way, right? So what is it we do in the top operations? As written here, we progressively add increasing levels of noise to the image, right? As you can see here, from here to here, there is a little bit of noise, more noise here, more noise here, more noise here. You can see some features of dog here, right? But when it comes to the final image here, it's completely noise. But somewhere there you have the information about this original image being present there, right? So the first action to be done in this diffusion model is, as the name itself indicates, we diffuse the content of the original input, right, by adding noise, where the level of noise increases from one step to the next step. Then what is it we are doing in the reverse process? We take this noise image as the input, right? Then progressively denoise that. That's basically content, reduce the content of the noise, right? And in the whole process, we are also generating an image, but that image is not same as the original image, but it's somewhat related to the original image, right? These models are what are called the denoising diffusion models. And again, there is a very nice review paper which is available, okay? And so there is a lot of work nowadays on
Pixels of second image.
sorry?
Is it noise or pixels of the second image?
No, we are going to get the pictures of second image.
Pictures of second image is slowly added.
No, 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 I'm not adding this picture. I don't have this picture at all.
Then what is the significance of noise adding?
Yeah, basically, I want to generate a new image from a given image. Okay? Like GAN is one of the types of techniques that one can use, right? But here I'm using a different technique. Okay? I'm not obviously going into details. What it briefly stated here is that I take the input image, okay? Then I increase the level of noise that's added to this image progressively, right? Then once I have this final image here, which is more or less completely noisy, but please remember that this image is generated from this image, right? Then I do some operations to reduce the noise here. But when I'm reducing the noise, I'm not just removing the noise there, I'm also doing some operations. So the result of those operations is generation of a new image, right? So depending on how you do this kind of cleaning of the noise, right, the type of the image that is generated finally will be dependent on that, but that finally generated image is somewhat close to the original input image, right? Please remember that the task here is how to generate new images, right? Varieties of problems, right? Especially in the medical image domain, where you have very limited amount of data available. Using that limited amount of data, you want to generate some new data which is somewhat related to the original data, right? That's where all this can be useful. Yeah.
But sometimes when generating a new sample, you may not even get a dog at all.
No, no, no. As I said, no, no. It all depends on how you do this denoising operation, right? So the denoising operation has to be done in such a way that you will generate the images of the same type, not the images of completely new type. Yeah. No, see there I have some training data where I have the images of the dog and the corresponding and the images of the cat and the corresponding images of the dog, and then I train the model using both these images, right? Here I am not doing that. Here I am giving only this image as the input, right? Then I want to generate some new images which are somewhat related to this. I am not even saying what is the kind of relation here, right? Okay. Again, as I said, I am not going to details. This is a new topic for research in the deep learning. Okay. So one has to go through those details. Okay. I think we are coming to the end of the whole thing. There are few textbooks available on this deep learning topic. They are what are listed here. I think a couple of them are available online, so you can try to download them and then use that. But unfortunately, not all these books cover all the topics that we discussed. As you can see here, many of these books are now 2016, 18, and by then the transformer models were not even proposed, right? And I think only this last last book has some discussion on the transformer models. But you need to refer to the papers, right, to get more details about the models as well as the applications of these models for the variety of problems, right? Again, the number of papers is a few tens of thousands. Obviously, I cannot list all of them, right? Depending on your area of interest, you can try to look for the papers, right? So what I wanted to do is just give an exposure to the different deep learning models that are being explored nowadays, right? And for what kind of problems related to the image and video and the text processing. But there are lots of papers on using the deep learning models for the other domains like audio and speech processing, medical image processing. Also, there are lots of papers for financial applications, right? Networks, computer networks. So the models are fairly generic, right? As long as you are able to map your problem onto this model, then you can go ahead and build this model-based solution for the problem that you are interested in. Okay. As I already told, you need to follow it up with the reading of the relevant papers, right, in order to kind of consolidate. The purpose of these talks is only to expose you to the topics and introduce you to the terminology, right? But I don't expect you to understand everything from this 4-hour session, right? So if you are interested in developing a good background of this, right, you need to follow it up with the reading of the relevant material. Okay. Yeah, I'll stop here. If there are any other questions, I'll try to take them. Yeah. No, no. I don't think there is any other model than the diffusion model where you can generate the new data by simply adding the noise and then denoising. No. The diffusion models are very specific type of models which are what is it you want? Semantic representations. No, no, I don't think the tools support any of this, right? See, the tools support the basic models, okay? You can use the tool to implement a CNN model. You can use the tool to implement a recurrent neural network. But if you want to develop a image captioning system, you need to, yeah. Of course, some of the authors of the papers, right, make their code available for you, right? That you can download and then use it. Yeah, typically most of these tasks are implemented for some benchmark data sets because I need to evaluate the performance of the models and then tell how well the models perform, okay? So when I want to write a paper, right, I need to do all the experiments on the benchmark data sets, then get the results, then say how my model is better than the existing models, okay? So for almost every task, there are benchmark data sets available, okay? I am not aware of that, but there must be a lot of work going on. Yeah. Okay. Any other questions? Yeah. No. Stack dot encoder is only for the deep feed forward neural network. Because we're talking about the pre-training for only the deep feed forward neural network, right? Unfortunately, you can't use the stack dot encoder for the CNN model because the CNN structure is completely different, right? Stack dot encoder is only for pre-training a deep feed forward neural network model, right? But you have the pre-training like the BERT model for the transformer models. Unfortunately, for the CNN models, there are no pre-training methods because it's a complex task. Yeah. Good. Any other questions? Okay. There are no other questions. Thank you for your attention. All the best.
Good evening. Good evening, yes. Good evening, everyone. I sincerely thank Professor C. Chandrasekharan sir for the wonderful session covering most of the topics in ML and DNN. Sir has addressed image classification, scene image classification, query-based query by example, query by semantics, image captioning, paragraph captioning, visual query question answering, expression comprehension, DNN, pre-trained models, autoencoder, LSTM, sequence mapping, text processing, BERT, attention models, and many more research fields and the models to solve such problems. So I thank you very much, sir, for sharing your immense knowledge. As you mentioned in the beginning, it is indeed an entire semester course what you try to share in 4 hours. Thank you so much. And now I request Professor Chairperson of the Department of Computer Science, HR Shashireka Madam, and Professor B.S. Shekhar, the FDP Coordinator, to present a memento to Professor C. Chandrasekhar sir as a token of gratitude. Thank you, sir. Dear participants, tomorrow we have industry visit. So all of you please assemble at 8:45 here in this venue. 8:45, sharp 9 will be leaving from here. So there are 3 teams we have formed because we have to visit 3 departments: oncology, dermatology, and incubator center. So we have formed 3 groups. That group information we will share in the group. So first group will be led by Shazia. Second group will be, Vanur Swami will be there in the second group. And third group I will be there, group A, group B and group C. So please assemble at sharp 8:45. This is compulsory for all the participants. Okay, because this is an opportunity for you to see what is the real image processing, practically how it is used and how it is done. If you go otherwise, they won't allow you to go to all these center. Even if they allow you somehow, they will not be explaining you all those things. So the guiding will not be there by the office, I mean hospital staff or professional. So this is an opportunity. Please make use of that. Please assemble at 8:45 here itself. Afternoon we will be having the session by Madam Shashireka. Okay, thank you. I will put the information in the group. Now we will be having a 30 minutes tea break. After that, lab session.